Beginning from this lecture, I will talk about how to interpret results from auto-regression models, specifically proportional odds model. So let me first talk about how to use odds ratio coefficients to interpret results. Okay, so if you remember my previous lectures, you would know that the probability for an ordinal response variable y equal to m given data and parameter is equal to a difference of cumulative density function, depending on the assumption about the distribution of the error term in the structural model for the latent y. We could have order logit and order problem model. Right? So this f varies with different error distribution. And the cumulative probability is defined as, well, what is cumulative probability? Cumulative probability is the probability that y smaller or equal to a certain response level, and it is sum of all the individual probabilities of y equal to j for j smaller equal to m. So for example, the probability for y smaller equal to 3 is what? Is the sum of the probability y equal to 1 plus y equal to 2 and y equal to 3. So here, giving you a very concrete example. How about the probability y smaller equal to 3, a given data and parameter? Well, it is equal to the probability y equal to 3 plus the probability y equal to 2 and the probability y equal to 1, right? Then what is the probability of y equal to 3? Well, according to this definition here, or what we derived previously, it is equal to a difference of 2 cumulative density functions. And what's the probability for y equal to 2? Well, again, another difference. What about the probability y equal to 1? Again, another difference. And we need to add up all these differences. Luckily, we have lots of cancellation. So here, all these terms are canceled out. And for this term here, this additional term, because tau 0 is actually negative infinity. Okay, usually we don't have tau 0. Tau 0 is defined as negative infinity. And the cumulative density function for negative infinity minus a finite number, it's still going to be the probability from, excuse me, the probability is going to be what? 0. So this term drops out. What we get is the probability for y smaller or equal to 3 is this single cumulative density function. To generalize, the probability y smaller or equal to m, that is the cumulative probability, is simply a single cumulative density function term. And if we're talking about order logit, then it is lambda. The lambda function basically goes like this, okay? So anything within lambda, we're going to become what? The exponential function of tau m minus x beta over 1 plus the exponential function of same thing, tau m minus x beta. So anything that goes into the lambda function goes into the natural exponential function in the numerator as well as the natural exponential function in the denominator. Okay, and so just to recollect, well, here, well, then this becomes a binary logit, right? Binary logit, okay? And the intercept is tau m minus x beta. Actually, beta 0 can be identified from this term, okay? What we'll have is intercept combined of tau m minus tau 0. And the tau m and beta 0 are unidentified, but the combined term is identified. And usually we would omit beta 0. Okay, we will use tau m as the intercept. And the slopes are negative beta k, negative beta k. So this is what we just derived, right? The cumulative probability function for y smaller or equal to m is this lambda term, cumulative density for a error term that follows a standard logistic distribution, and that's its functional form. And using methods for binary logic, the odds of y smaller or equal to m, odds of y smaller or equal to m versus y greater than m, given x is expressed like that. Okay? And from here, this term, we can derive this equation, the natural exponential. So the odds of y smaller equal to m, odds, okay, versus y greater than m is the natural exponential of tau m minus x beta. Then the odds ratio for a change that is 1 unit change in x, if you carry through the computation, it becomes the natural exponential of negative beta k. If you remember how the odds ratio is calculated in binary regression models. Here, the interpretation is a little bit awkward because we have to use natural exponential of this negative beta k. So this is not very convenient for a lot of users. So people think, well, how am I going to change that negative sign into positive sign? Yes, we do have a way. Okay, so this is what we have in our last slide, right? So the odds for a change, the odds of y smaller equal to m over y greater than m is the natural exponential of negative beta x. Alternatively, or more popularly, if we slip the numerator with denominator, that is the odds ratio here. Excuse me, the odds here, right? But if we flip these two terms, if you recall, recall that the previous odds is the probability of y smaller equal to m over y greater than m. Now we flip this odds. So in the numerator is the probability y greater than m. In the denominator is the probability y smaller equal to m is equal to negative tau m plus x beta. Recall that for the previous odds, the odds of the probability y smaller equal to m over the probability y greater than m is the natural exponential of what? Of tau m minus x beta, right? After we switch the numerator with the denominator in this odds, then the natural exponential becomes negative tau m plus x beta, plus the x beta. Then the odds ratio for a change, for a unit change in xk becomes what? The exponential, natural exponential of beta k. So now it becomes a positive sign, okay? So this again is from our last slide, right? The result we got from our last slide. So how to interpret this result? Well, we're going to say for a unit increase in xk. So this is slope coefficient for xk. Okay, so for a unit increase in xk, the odds of outcome being greater than m, okay, as opposed to smaller or equal to m, is changed by the factor of e raised to the power of beta k, holding all other variables constant. And you can go through, actually, you can go through derivation from here, okay? From here to interpretation we have here. Okay? Okay, so that's for odds ratio interpretation. Here, I only talk about interpretation of odds ratio coefficients for continuous variables. And for binary indicator variables, it's kind of similar to the interpretation of the slopes or coefficients for binary indicator variables from binary regression models, right? Okay, so you're going to say, well, being female as opposed to being male increases or decreases the odds by how much, depending upon how the dummy coding you have.